right, so we're going to answer these questions regarding independent events. But before we begin, what the heck are independent events? So remember, independent events are events where they don't impact one another. So for example, let's say I have a coin and then I have a die, right? So if I flip that coin and let's say it lands on heads, is that going to impact the chances of that die landing on, say, a 3? No, right? Those two events are totally separate. They are not going to impact one another. So that's what we're looking at when we're talking about independent events, right? Two events that have no influence, right? No type of impact on one another. All right. So we're going to look at the equations that go along with these independent events. All right. So let's dive in here. So assume, for this first question, assume that a student is chosen at random from a class. Determine whether the events A and B are independent, mutually exclusive, or neither. All right. And if you haven't watched our video about mutually exclusive, all that means is that mutually exclusive events, they can never occur at the same time. That's different than independence, right? So mutually exclusive events, they can never happen at the same time. So if I flip a coin, it can't be a heads and a tails, right? It has to be one or the other. Can't be both. All right, so here we go. Here's a question. Event A, the student is a man. Event B, the student belongs to a fraternity. So we know these are not mutually exclusive events because you can be a man and in a fraternity. And if you don't know what a fraternity is, that's just a group of, usually it's guys, right? Men that have something in common. So usually in college, they're part of a group where they have something in common, right? And so these events are dependent on one another because if you're a man, that is going to increase your chances of being in this fraternity, right? So these are not independent events. These are actually dependent events because the chances of you being in a fraternity increases if you're a male. So in this case, this answer would be neither. It's not mutually exclusive, nor is it independent. All right, so let's look at some numbers now. Let's look at another example where we actually have to make some calculations. Follow me. All right, so let's look at some numbers. So it says, for this example, let A and B be events, all right, with the probability of A taking place is 0.3. The probability of B taking place is 0.6. And the probability of both of them happening, right, A and B taking place is 0.03. So our first question says, are they independent? So when we're looking at independence, what we're going to check for is for these to be independent, what we're going to see is that the probability of A and B must be equal to either the probability of A times the probability of B given that A is taking place, right? That's one of our formulas that we're going to be looking at, or the probability of B times the probability of A given that B has taken place, right? Or the probability of A times the probability of B. And we could use that one if we know that they're independent right off the bat. All right, so in this case, let's look at what we're given. All right, so we definitely have the probability of A and B. They tell us that's 0.03. So 0.03, and what we're going to do is we're going to check. Notice they give us the probability of A and the probability of B here. So we're going to go ahead and multiply, right? We're not given these conditions here, so we're not going to use these two formulas up here. So we're going to use this one down here because that's what we're given. We're given the probability of A and we're given the probability of B. So the probability of A that they gave us is 0.3. And the probability of B that they give us is 0.6. So when we multiply those, we're going to see that these two, when you multiply them, does not equal 0.03. So that's our quick little check, right? These are not equal. So what this tells us that these events are not independent, because if they were dependent, right, whatever those two events may be, then when I would have multiplied the probability of A times the probability of B, what that would have produced, boom, this number right here, 0.03, and it didn't. So again, that's how you're going to check to see if these events are actually independent or not. So that's how you check for independence when they give you the formula. You just multiply these two, and it better equal the probability of A and B. All right. So now what it wants us to do for part B is to compute this OR statement, right? So when you're doing an OR statement, then our formula here is the probability of A plus the probability of B. All right, it's a tongue twister with all these probability words, minus the probability of A and B. All right, so that's our formula for an OR statement. That's using our addition rule here. And notice they give us the probability of A, they give us the probability of B, and then they give us the probability of A and B, which is right here. So let's go ahead and plug that in. So we got 0.3 plus 0.6, which is going to give us the 0.9 minus the 0.03, which is going to give us the 0.87 right there. All right, so there's a probability of A or B. All right, and this last question, it says, are A and B mutually exclusive? Now remember what mutually exclusive means. It means that the probability of both of those things happening at the same time is 0. So here they're telling us that the probability of A and B happening is 0.03. While that's not 0. Yes, it's small, but it's not 0. So the probability of A and B, are they mutually exclusive? No. Right? So for part C here, let me write it down here for you. They are not mutually exclusive, and the reason is because the probability of A and B, they do not equal 0. So make sure you have that down. If they were mutually exclusive, the probabilities of both of them happening would have to be 0. All right, follow me to our next example. All right, so in this case, let's say you have a coin, a fair coin, and it's going to be tossed 4 times. All right, so what is the probability that all 4 tosses are heads? Right, so we're trying to find the probability that the first toss is a heads, that the second toss is a heads, that the third toss is a heads, and the fourth toss, that every single toss there is a heads. Well, let me ask you this. Are these events independent of one another? So what I'm really asking you is, if I flip that second coin, right, is that second coin going to impact the result of the third coin? Absolutely not, right? If I flip that first coin, is it impacting the next coin? Absolutely not. So these events here, all of them are independent of one another, right? So because they're independent, what that means is that I could just multiply every single one of those events. So that's what I'm going to do here. I'm just going to multiply every single one of those events, because that's what this probability is going to equal, because they are independent. All right, so now what's the probability of getting a heads, of landing on heads? Well, it's 0.5. What's the probability of landing on heads? It never changes. It's always 0.5. So all I'm doing is I'm multiplying 0.5 times 0.5 times 0.5 times 0.5, right? Another way you could write that, if you wish, is 0.5 raised to the 4th power, and do that in your calculator. Some of you, your teacher might have you do 1/2 raised to the 4th power, which is the same thing as 1/16. And of course, we could plug that into our calculator and round to 4 decimal places here. So again, whatever the instructions are, make sure you read them. And in this case, we'll round this to 4 decimal places. All right, so let's write our answer and let's move on to our next example. All right, so in this example, what happens if a dice is thrown twice? Find the probability of getting 2 5s. So what's the probability of getting a 5 and a 5? Well, once again, if I roll a die and it lands on a 5, is that going to impact my chances of rolling another 5? Absolutely not. So these events are independent. So that's why I'm going to find the probability of rolling a 5, and I'm going to multiply it times that same probability of rolling a 5. So you could do this once and then square it, or you could just go ahead and calculate these and multiply them. So chances of you getting a 5, well, there's 1 5 out of those 6 sides. And again, same thing if we do that again. So we multiply it, so we end up with 1 over 25 there. And again, just plug that into your calculator to get your probability. Making sense? Good. All right, mathletes, so now it's your turn. Let's see if this really makes sense. So here's a question. It's a little different, but the same exact idea. So you have 2 sets of bags, right? And the cards with a letter on each card are as followed. So we have all these cards with a different letter on them, and they're placed into their own separate bag. So you're going to pick each card, you're going to pick 1 card from each bag, right? So for part A, you're going to comment down below, what's the probability, right, that she picked the letters J and R. So a J from the first bag and an R from the second bag. So you're going to find that probability. So if she picks a J from the first bag, is that going to impact the chances of her getting an R from that second bag? No, right? They're 2 separate bags. So these events are independent of one another. All right. And then part B here is saying both letters that she chooses from separate bags are Al, right? So again, whatever she picks from that first bag is not going to impact her chances from that second bag. So again, what we want you to do, comment down below and leave it as a fraction. Leave your answer as a fraction here, just so we could see how well you did. All right, mathletes, so hopefully this was helpful. Don't forget to like this video, subscribe, and tell friends and family what we're doing here at Dr. Math Studios to help you out. All right, mathletes, have a great day. Peace.